Good afternoon, everyone, and thanks for joining our Magnetosphere Online Seminar Series again this week. It is officially afternoon, just a couple of minutes now, and I want to get started and jump in here and introduce our speaker for today, which will be Dr. Alex Glocer from Goddard Space Flight Center, who's a civil servant working with global MHD models to understand magnetosphere ionosphere coupling, specifically with a focus on ion outflow, which is going to be the subject of his talk today, and will be kind of a nice follow-up from a talk given earlier that we had a couple of weeks back. So we're definitely looking forward to that as well. So with that, Alex, without further ado, I'll give the ball over to you, and we're looking forward to your presentation.
All right, thank you very much, Jason. Give me just a moment to share my screen. All right, well, thanks again for that introduction, and I appreciate the invitation to talk today. So the topic of this seminar, as Jason said, is modeling ionospheric outflow and its consequences. And so this is work I've been doing in a couple of different projects, and I'm going with different collaborators, and I'll make sure to acknowledge them in the individual sections. Just a second. So as an outline, I'm going to start off with just a little bit of motivation, talk about what is ionospheric outflow and what consequences does it have. And if you saw Rick Chappel's talk a couple of weeks ago, you probably already have a lot of this in mind, but for those of you who missed it, I'll go through some of the motivation again. I'm also going to give an overview of the modeling approach. And then I'm going to talk about two specific studies. So the first is on ion outflow in particular, and how does ion outflow scale with different energy inputs, sort of a modeling study of that. And then we're going to look at what happens to that outflow when it gets out into the magnetosphere and what does it do. And to do this, we're going to look at a specific case study of ion outflow during a storm. And then I'm going to end with some discussion of some new model developments, including implementation of Lagrangian Remap and improved Plasmasphere coupling. And then I guess we'll take any questions. So I know that this is the Magnetosphere, seminar, and so everyone here, should know what the magnetosphere is, but I think it's still a fitting way to start, especially if there are any students who are joining for the first time. And so the magnetosphere, we're talking about this cavity carved out of the solar wind by the Earth's intrinsic magnetic field. And, it's a very dynamic environment, as you've seen in many of the other seminars here. And I think is well illustrated by this movie from the NASA Science Visualization Studio. It's an illustration from a Bats-R-Us simulation. And what I'm going to talk about is a little bit about the dynamics, but mostly I'm going to talk about where the plasma in the magnetosphere is coming from. And so in the magnetosphere, you have two sources of plasma. You have the solar wind, which is blowing in from the sun constantly and is providing protons to the magnetosphere. And you have the ionosphere, which is providing protons as well as heavier ions such as oxygen and N+, NO+, other species as well. And so, where the plasma comes from can have some significant impacts for the magnetosphere as a whole. So I'm going to walk through a couple of examples of that. So in the inner magnetosphere, where you have the ring current and radiation belt region, you can find that during storms, a lot of times the plasma in this region is coming mostly from the ionosphere. And so this is an example I like to show from a study from Nose et al. In 2005, where they're looking at the strength of the ring current during different storms and looking at how much energy in the ring current is contributed by the O+. So O+ here is very nice because it only comes from the ionosphere, and so it's a clear marker of an ionospheric source of plasma. And so what you see is that for stronger events, you're getting a larger contribution of ionospheric plasma. And so if you want to understand the magnetosphere and where the plasma comes from during strong events, you have to understand the source from the ionosphere. the internal source of plasma. So it's not just important for the ring current, it's also important for the reconnection dynamics. So at the upstream magnetopause, you have day side reconnection, you have night side reconnection, the magnetotail. And we know that the presence of O plus can affect the ionospheric outflow. And so this is an example of that from a paper by Shea et al. Showing the difference in the reconnection rate with and without O plus. Also, we see this in MHD simulations of the magnetosphere, that the inclusion of ionospheric outflow can change the dynamics. And this is just an example of the outflow arriving and the resulting plasmoid forming in the magnetotail. Now, when I talked a lot about O plus, which, as I said, is very nice, as it is a clear indicator of the ionospheric source of plasma, but there are also protons coming out of the ionosphere, and they can supply actually quite a lot, filling up the magnetosphere from the inside. And so one of the things we're going to look at is how much plasma how much of the proton population comes from the ionosphere and how much comes from the solar wind. Now, I want to transition from this introduction to talk about the modeling tools that I'm going to use in this study. And so I'm going to use the modeling tools developed at the University of Michigan, the Space Weather Modeling Framework. And so this is a very comprehensive system of models, that goes all the way from the sun to the Earth. And what I'm going to use is a subset of these models that covers the part of the chain that I'm focused on in this talk. And in particular, I'm going to use this subset. So I'm going to start with the global magnetosphere model, which is the BATS-RS code. I'm going to use the multi-fluid version of that. I'm going to use the polar wind outflow model, which I've been developing for a number of years to represent the ionospheric source of plasma. And I'm going to use the ring current model, SIMI, which is developed at NASA Goddard by Mei-Ching Fok, and I contribute to that. And we're also going to use the ionosphere electrodynamics model as well to represent the MI coupling from the electrodynamics side. Now, of particular relevance to this presentation is the ionospheric outflow. And so here I'm going to use the polar wind outflow model, which I've been developing for a number of years. And the polar wind outflow model, or PWAM for short, solves the transport of plasma from the topside ionosphere into the magnetosphere, starting just below the F2 peak, around 200 kilometers, and goes up to a few RE in altitude. And so we get a single solution along a single field line, but we solve for hundreds of field lines, which move those field lines around, and that lets us reconstruct the 3D global solution. So now along each one of these field aligned solutions, we're solving the equations. We have a setup like this. So basically at low altitudes, we're solving the hydrodynamic equations for each ion fluid. And then we transition to this hybrid PIC or DSM with Monte Carlo collisions using direct simulation Monte Carlo at high altitude. And then we interface these two approaches at an interface, which is in the transition region. We're also including the superthermal electron population, and then a separate superthermal electron population using the two-stream approach at low altitude and collisionless kinetic mapping at high altitude. And then we have a thermal electron population, which is enforcing quasi-neutrality, current conservation, and we solve a separate energy equation for that population. And all of these disparate plasma constituents are tied together with a generalized Ohm's law, which lets us get the parallel electric field. So a little bit more detail in the hydrodynamic solution at low altitude, we're solving the gyrotropic 5-moment multifluid equations with heat flux. We're solving for O+, H+, and helium+. We're including, the sources of these ions, from chemistry and photoionization source terms. And we include the collisional coupling of the different ion fluids with each other and with the neutral background through collisions. For the kinetic solution at high altitude, instead of fluid equations, we're solving for the gyro-averaged particle equation of motion. And we're getting, for each fluid population, we have a corresponding ion particle population. And we also include the collisional coupling between the different species using the Monte Carlo approach, and also including resonant wave particle interactions. Here I'm showing we're using relations from Barkut and Barghouti, but we have some other ones that we're using as well, including one I'll use a little later from Crew et al. And finally, we include particle splitting and joining to try and control our statistics. So these are, basically we can split particles apart or join them together in order to meet a target number of particles per cell. And this will be very important later in the presentation when I talk about the implementation of Lagrangian Remap. So that's enough about the model description. And so I'd like to talk a little bit about applying the model to study ion outflow. And to start with, I'm going to use just some Plume simulations to look at how does ion outflow scale with energy input. And so the motivation for this particular study is some empirical studies done with FAST that were published by Bob Strangeway, where it was looking at multiple passes of FAST in the cusp region and looking at how does ion outflow correlate with Poynting flux and with electron precipitation. And with both of those energy inputs, one electromagnetic energy input, another particle kinetic energy input, you see that there's pretty significant correlation between them. And so the motivation here is let's use the model to try and understand the causal relationships that underlie these correlations and get a better understanding. And so this is work I'm doing together with Lars Daldorf, and we finished the work now. We're just trying to get the paper written up. And so, there's a lot of uncertainties in the empirical relationship. And in particular, there seems to be, we have some questions that we want to address. We want to understand what sets the lower limit of the ion outflow, what sets the upper limit. We want to understand, is this acceleration different for different species? For the same energy inputs, how are the different species responding? And then we also want to understand, how does illumination and precipitation factor into these empirical relationships? Is it different for solar maximum versus solar minimum, for example? So in terms of what sets the upper and lower limits, one of the things that I found pretty useful when doing this work is to think about what could be doing that. And so one possibility for the lower limit is the polar wind. The polar wind is flowing out all the time and is not as affected by some of these energy inputs. But there's also an interesting concept of the limiting flux, and this is discussed in a lot of detail by Richards and Tor and references inside of that paper. For H+, basically taking the production rate times the region of production, and that tells you, the limit in which the ionosphere is evacuating the plasma as fast as it's produced. So, this is a well-developed concept for H+. You can imagine a similar definition for O+, where you take the production rate as a function of altitude and then integrate above some altitude, and that can give you an estimate of how much O+ can be provided from the ionosphere. Basically, if you assume that things escape as fast as you produce it. Now, in this study, the way we set it up is we're going to consider a magnetic field line on the day side that's in steady state. And it's just going to enter the cusp region. And when it enters the cusp region, we're going to turn on wave particle interactions. And in particular, the mode of interaction we're assuming is the ion cyclotron resonant heating. And we're going to sweep the wave amplitude over the course of multiple simulations. We're going to start with very weak wave power, and we're going to do the simulation again with stronger wave power and again with stronger wave power. And we're going to see how the outflow scales with that energy input. And we're going to repeat this for different solar ionizing fluxes, so different solar EUV input. And we're going to repeat it for different precipitation. Now, as we increase the solar UV input, we're going to change the thermosphere background, but we're also going to change the ionization rate and the production rate, which is going to affect the limiting flux. And the same with the precipitation. The precipitation will give you additional heating, but it will also give you additional ion production. So this is an approach that was inspired by a paper from Zeng and Horowitz, and we're kind of building on that approach by introducing these other factors into the simulation. So this is one example for solar maximum. And on the x-axis, I'm showing the strength of the waves, and the y-axis, I'm showing the log of the ion flux. So this is the ion outflow response to different wave powers. And so I'm showing you the O+ flux in blue and the H+ flux in red. And what you see in this simulation is that you do in fact have a power law relationship in the outflow once the waves exceed a certain threshold value. And that type of power law relationship is what we expect from the empirical relationships that were published before. Now, there at the lower end, you have the sort of base flux that's set by the polar wind H+, that you just don't, you never get less than that value. But at the upper end, you get limited. After a point, if you put more and more energy in, you don't get more O+ out. And so this is just a crude estimate of the O+ limiting flux. I think it's actually a low estimate. But the point is, at some point, you are going to saturate, and it doesn't matter how much energy you put in, you're limited in what you can get out. Interestingly, the H+ flux, even though the H+ gets accelerated, there's a limit to how much H+ you can provide in the absence of precipitation, and you're already coming out at fairly close to the limit. Now, if you introduce some soft precipitation, things change. So here we introduce some soft precipitation, and that's going to give us additional ion production, additional ionization, additional heating. And we see that the limits are going to change, and you're able to get more O+ out than you were before. The power law relationship is going to change. And also how the H+ and the O+ respond to that energy input is also going to change. And so if you have both soft precipitation and wave power going on at the same time, the relationship is different than if you only have one occurring or only have the other occurring. Now, the next iteration of this is to do it for solar minimum. So this is with a low solar ionizing flux. And qualitatively, the picture is quite similar to before. But again, the limiting, the amount of O+ you can get out is lower than in the solar maximum case because you're producing less at low altitude. But the same general picture holds that when you introduce the soft electron precipitation, again, you're going to change the power law relationship and you're going to change how the different species respond. So this is just a sampling of the different cases that we've looked at, but I think the conclusions are, that the lowest limit of the flux that we see seems to be set by the polar wind, definitely when there's no precipitation. And there definitely is a limit on the upper O+ flux that you can expect. You just can't pull out more O+, after a point. If you change the solar ionizing flux, or if you change the precipitation, that's going to change the range of the outflow that you can get. It's going to change the power law relationship that you will obtain. And it will also change how the individual species respond. So that's where this study is. And, there's some caveats, of course. There are other mechanisms that are occurring at the same time. We're not including Joule heating in this, for example, or other wave modes. On the night side, the scaling relationship could be different, especially if you're considering a field line that's entering the auroral region. You're going to have a very different initial condition than a field line entering the cusp, and very different precipitation characteristics. So this is a study that's done specifically for the cusp, but you could have a different set of relationships for night side type outflow. So with that, I want to move on to the second study. And so the second study is going to talk about the origin of near-Earth plasma. And so here I'm going to use Plume again to provide the outflow, but I'm going to use this as part of the global, space weather modeling framework, to look at the impact of ion outflow on near-Earth space. And so here I'm going to focus on a particular geomagnetic storm, this June 2013 event. And I'm going to look at a number of questions. And I'm going to go ahead and give you those questions and the answers right up front, and then I'll show you how we got there. So the first question in this study is, where do the protons in the magnetosphere come from? And the answer is that, many, at least in this particular case, come from the ionosphere. The second question is, the outflow that's coming out is very cold. So can this very cold outflow turn into the hot population in the magnetosphere? And the answer is yes, and I'll show you that. We're also going to look at what's the role of hemispheric asymmetry in ion outflow. And as you'll see, when we introduce asymmetric ion outflow, you're going to get asymmetric composition in the magnetosphere, and that can affect the dynamics. And finally, we're going to look at what impact the plasmasphere can have on the composition and dynamics of the magnetosphere. And in particular, you're going to see that when we introduce the plasmasphere, you can end up reducing the day-side reconnection rate. This will result in a decreased solar wind magnetosphere coupling, which will suppress the outflow and change the ring current intensity. So this work was all published recently in a paper. Here's the reference and the co-authors on the bottom. So if you want to see more details, you can look into that there. And so, as I said before, I'm doing this study with the space weather modeling framework, and I'm using this setup here. So this is a subset of that larger picture that I showed you earlier. And in this case, the ion outflow, as I said, is provided by Plume. Plume is setting the inner boundary condition of the BATS-RS magnetosphere code. In this case, BATS-RS is configured to solve the multi-fluid MHD equations with one fluid for solar wind protons, one fluid for ionospheric protons, so we can separate those populations, another fluid for ionospheric oxygen, and then a separate fluid for the cold plasmasphere population. Now, BATS-RS is coupled in the intermagnetosphere region with the SIMI code, and we've improved that coupling in this paper in order to do multi-fluid coupling. So we're having each of the fluids in BATS-RS is coupled to a separate species in the SIMI code to let us capture the effect on the ring current from these different populations. So, some other features of this study are that we're introducing now separate hemispheric outflow solutions. So the northern and southern outflow solution are solved separately, and also setting the inner boundary conditions of BATS-RS separately as well. So if you have asymmetric ion outflow, you'll get asymmetric provision of that outflow to the magnetosphere. And we've expanded the SIMI coupling, as I've said. So to test the effect of Plasmasphere, we actually did our simulations twice, once with no Plasmasphere included, and another with a very full Plasmasphere, um, to test these two limiting cases. So we'll talk more about that a little later. So going back to question one, where do the protons in the magnetosphere come from? So as I showed in the introduction slide, you can get them from the solar wind or from the ionosphere, and the ionosphere can provide quite a lot of them. Um, and the issue is when you observe protons in the magnetosphere, you don't know where they came from. They don't wear name tags. You can't look at one and say you're a magnetospheric. This magnetospheric proton is from the solar wind, and this other one is from the ionosphere. So when people do data studies, they try and get at this in a couple of different ways. So this is an example from Glocer and Hamilton, where they were using AMT data, assuming that the solar wind proton to minor species ratio in the solar wind is the same as in the magnetosphere. They can find, one potential answer to this question. And in some locations, the ionospheric contribution of protons can be quite significant, exceeding 50%. There's another way that people try to get at this. So this is, from a study from Shelley et al. And also discussed in Bill Peterson's paper, where they're assuming that the ionospheric H plus to ionospheric O plus ratio in the outflow is going to be the same in the plasma sheet. And there's a few other assumptions in there as well, but basically if you make those assumptions, you can find that during active times, you can have quite a large contribution of ionospheric protons to the plasma sheet population. So these are data studies, but what I want to do is come at this same question, but from a modeling perspective. So using the modeling network that I talked about earlier with the space weather modeling framework, we're trying to get at this. And so here I'm showing you the y=0 plane. This is the noon midnight meridional plane. And I'm showing you the ionospheric protons in the upper right, the ionospheric oxygen in the upper left, and the solar wind protons in the lower left. And so this is showing, the color contour is showing the percentage that each population is contributing to the total. And so during the storm main phase, we find that the lobes are largely filled with ionospheric plasma, and that the solar wind is providing, quite a lot, in fact, the majority at this time of the plasma sheet and intermagnetosphere population. Now, as we go into the storm peak, we find that, at least in this cut, that we're displacing quite a lot of that solar wind protons and replacing it with ionospheric plasma in this simulation. But this is a dynamic problem. And as we enter the storm early recovery phase, we start getting new injections of solar wind protons into the plasma sheet and eventually into the ring current. So it's a very dynamic situation for this storm. But the ionospheric population definitely contributes a fairly large portion of the plasma. So now I want to go to question two. We see that the ionosphere contributes a lot of the plasma, but this plasma that comes out of the ionosphere is cold initially. And so can this turn into the hot population? So Rick Chappel talked about this a couple of weeks ago in this seminar, showing these test particle simulations from Matthew Huddleston's paper using Dominic Delacour's test particle code. And so this is one example of a particle trajectory that's coming out very cold. The energy is shown on the bottom. It's less than 10 eV when it comes out. And as it traverses the lobe, it eventually encounters the equatorial plane and the midtail, the crosstail current sheet, and gets picked up and accelerated very rapidly over a short period of time. And so it goes from a tens of eV particle to a 10 keV particle very, very quickly. And so this was a study done with test particles, but actually you can get a very similar picture if you in the multi-fluid simulations as well. So here what I did is I took the multi-fluid simulations and I started launching particles. Now, these aren't true particles. This is more like dropping quarks into the stream, and they're, following the flow of the H plus ionospheric H plus population. And what I did is I color code the surface of each of these quarks with the temperature of that population. You see that they're coming out at similarly at 10 eV or less. And when they encounter the crosstail current sheet, they're getting picked, the crosstail electric field, they're getting picked up very quickly, and they get heated very rapidly, just like in the Huddleston paper that I showed you before. And then they come around, they form the warm plasma cloak as they come around on the day side. Now, that's showing you that this cold population can turn into a hot plasma sheet population, but they can also contribute a lot to the very hot ring current population. And so to illustrate that, what I did is I took the output from the SIMI model that's that's providing the ring current representation, and I integrated the total energy content associated with each species. So I just went ahead and I summed up how much energy is contributed by solar wind protons in the ring current, how much is contributed by ionospheric protons, how much from ionospheric oxygen. And then I track that value over the course of the event. And during the early phase of the event, it's mostly contributed by the solar wind protons. But later in the event, the ionospheric oxygen and ionospheric protons become quite important. And at some point, you can say that the ionospheric contribution is outstripping the solar wind contribution. So even in the ring current, it can be quite substantial, and not just for O plus, but also for H plus. So for the third question in this study, what's the role of hemispheric asymmetry in ion outflow? So here, as I said at the beginning of this section, we're including a separate outflow solution for the northern hemisphere and the southern hemisphere. And for this event, we have significant seasonal asymmetry. We have a northern summer condition and a southern winter condition. So we have asymmetric conditions of illumination. And so what we find then is that we get stronger O plus flux and stronger H plus flux in the northern hemisphere. And we get weaker O plus flux and weaker H plus flux in the southern hemisphere. Now, if you look carefully at the color bars, you see they're not exactly the same. And so if you pay attention to that, you see that actually the O plus is much more strongly affected than the H plus. And so this means that you get more outflow in the northern hemisphere, more total outflow, and a higher fraction of that is O plus. You get less total outflow in the southern hemisphere, and a larger fraction of that is H plus. So this difference in the outflow solution is going to manifest itself in the magnetosphere. And in fact, you do see that. You see that you have more O plus, that the outflow coming out of the northern hemisphere is more O plus rich, and the outflow coming out of the southern hemisphere is more H plus rich. That's going to give you asymmetric filling of the lobes, but it's also going to mean that at the night side reconnection site, you're going to have asymmetric composition on either side of the X line as a result of this asymmetric outflow. So now the final question of this section of the talk, I want to address what impact the plasmasphere can have on the composition and dynamics of the magnetosphere. So in SIMI, I've mostly been talking about the ring current modeling aspect of SIMI, but SIMI also models the radiation belts, and it also models the plasmasphere. So for the ring current, this is the very hot population, greater than 1 keV, and it's carrying most of the pressure in the inner magnetosphere and is very important for the force balance. On the other hand, the plasmasphere is very cold. It's, less than a few eV, but it carries most of the density in the inner magnetosphere. And so in past studies, when we couple the ring current and the MHD code, we only feed back the ring current population. We never feed back the plasmasphere. But now that we've expanded the coupling for multi-fluid MHD, we can feed back the cold population to a separate fluid. So now we can get the effect of both the hot population and the cold population, feeding back their contributions to different fluids, and capture both effects. So when we do that, we find that once the storm gets going, we start to create a plasmasphere drainage plume. So here this is a top-down view showing different isocontours of the density, and you see that you're getting this plume that's drawn out towards the day side and encounters the magnetopause. And if you look on the right, this is sort of a looking from the upstream direction, and this surface is the open-closed field line boundary in the code. And what I've done is I've painted on that surface the total density on that surface, and you get this enhanced density where the plume is encountering the subsolar magnetopause. Now, what I've also done is I've extracted the reconnection separator and the magnetic nulls in the simulation, so you can see where the reconnection is happening along the magnetopause. And in fact, you find that this enhanced density is occurring right in the region of the reconnection separator on the magnetopause. And so it's been discussed in previous studies, such as from some work from Joe Borowski and others, that when you get this enhanced density from the plasmasphere at the subsolar point, this can reduce the reconnection rate locally and possibly reduce the solar wind magnetosphere coupling. And in fact, we do see that in the simulation. If we can use the cross-polar cap potential as a proxy for the global reconnection rate. And we do the simulation without a plasmasphere in blue and with a plasmasphere in orange. And if you look before the time of the plume arrival at the magnetopause, you see that the cross-polar cap potential is very similar in the two cases. But after the plume arrives at the magnetopause, you get a significant divergence between these two cases. And in fact, when you include the plasmasphere in the simulation, you find that the reconnection rate is significantly suppressed by using this proxy of the cross-polar cap potential. Now, one of the interesting things that you can get when using global models to study this is you can start looking at system level impacts. And so it turns out that when you include the plasmasphere and you reduce this reconnection rate, that's going to have large system-wide impact on other parts of the space environment. So for example, if you look at the ring current here on the left, on the top, I'm showing the ring current pressure in the equatorial plane for solar wind protons, ionospheric protons, and ionospheric oxygen without a plasmasphere on the top, and then with the plasmasphere on the bottom. And what we find is that the ring current intensity is significantly reduced when we include the effect of the plasmasphere. And this is largely because we're reducing the efficiency that we can transfer solar wind energy into the magnetosphere. And that's going to reduce the ring current buildup. But it's also going to change the composition in the ring current. Whereas when we had the plasmasphere, it was largely ionospheric O+ contributing. When we include the plasmasphere, it's largely ionospheric H+ that's contributing to the ring current. So you can get a very different effect by including this cold population. Now, not only that, but you're changing the supply of plasma to the magnetosphere. So on the right, I'm showing the integrated fluent. So this is the total number of particles coming out of the northern hemisphere for O+ in blue and H+ in orange. And I'm showing it with the plasmasphere on, or without the plasmasphere on top, and then with the plasmasphere on the bottom. And what you can see is when you include the plasmasphere, you end up suppressing the total amount of outflow, and in particular, reducing the amount of O+ outflow that you get. So this is, really a system-wide impact that if you reduce the reconnection rate, you reduce the efficiency of the solar wind magnetosphere coupling, and that's going to reduce the amount of outflow you get, change the composition of the outflow, and also change the ring current buildup and composition as well. And so this is, I thought a very nice result and kind of shows the utility of system-wide integrated models, to study some of these questions. So just to summarize this study, we looked at where the protons in the magnetosphere come from. Many of them come from the ionosphere in this case. Of course, other storms may be different. We looked at how the cold ionospheric outflow can turn into the hot population. It definitely can, both in the plasma sheet and in the ring current. We looked at the role of asymmetric ion outflow and found that it can give you asymmetric filling of the lobes. And we also looked at the effect of the cold plasmasphere and that it can be fairly significant. So I'd like to finish up the talk by moving on from some science studies and talk about, the future a little bit. And what are some new model developments that I've been working on, that are coming down the pipe, and can lead to some improved future studies. So the first one I want to talk about is Lagrangian Remap. So now, to motivate this, I told you at the early part of the talk that in Plume we're solving for multiple magnetic field lines. And when those field lines are moving around the polar cap, and then we reconstruct the 3D solution. Now, so that's very nice because it simplifies the numerics in many ways, but there's some problems with that. And in particular, if you don't have enough field lines, so on the left, this is a case with a relatively small number of field lines, 125. And so this is looking down on the polar cap with looking at the effect of a cusp, an imposed cusp. And what we find, is that we get in general the right solution, but it gets kind of choppy, that if you have coarse resolution, you can only poorly resolve outflow structures. Now, one way you can address that is just have more field lines. And so on the right, this is a simulation with many more field lines. This is 900 field lines. And now the features are much sharper and they stand out much better. But it's still possible with this Lagrangian approach that your grid can tangle, that you can get bunching of field lines together, and you can get some regions that end up being over-resolved and some regions that end up being under-resolved. And so, there's two possible solutions to deal with this problem. So one is you can switch to an Eulerian grid instead of this Lagrangian approach. And the other is you can resample your grid periodically, this Lagrangian regridding, or sometimes Lagrangian remap, it's called. And so this second one is what I've started to implement in Plume. And the approach is relatively straightforward. So here you can imagine that you have a simulation and the field line foot points are shown as these green dots, in the polar region, on the left. And, after some delta t, you move the field lines, as a result of a combination of convection and co-rotation to new foot point positions. And so that's shown by these red dots. So on the right, the green dots are the initial location and the red dots are the new location of the field line after they've moved. Now, the idea is we want to be able to remap our grid points or resample our grid points back on our original distribution and try and maintain a nice uniform coverage of the outflow solution. So to do that, we develop a triangulation on the surface of the sphere based on the moved points. And so now I can choose any one of my remap grids, and I can identify, well, which triangle am I in? And I can try and interpolate back to my remap point. Now it's a little bit complicated because the field lines can be on different processors. And so you have to make a remap plan. You have to figure out, can I remap this point? And if I can, how do I do this while minimizing the communication between different processors? And so but the basic approach is that, once you know which line is being remapped, so like on the right, you know what triangle you're in. So I know in this case that I need to take field lines A, B, and C and use the information on those points to resample a new point at my remap location. And so here I can get my interpolation weights based on the subtriangles inside. So once I have my remap approach and I know which field line I'm going to resample, I can now basically interpolate. So I can say, take the different weights and I can, get a new field line. And so for the lower region of the field line, which is all a fluid code, it's relatively straightforward. I can basically get my new state variables from my old state variables just by summing up the different vertices of the triangle and multiplying by the interpolation weight. So that's straightforward. But for the hybrid pick region at high altitude, it's actually very challenging because, how do I interpolate the different particle solutions in order to form one combined particle solution? And the way I end up doing that is I end up taking the particle list from each field line and combining them into one particle list where I've adjusted the statistical weights of the particles by the interpolation weights. And so this gives me a much longer particle list, but all of the statistical weights are adjusted by the interpolation weight so that I get a sort of, true combination of these different particle populations. But now the problem is I have way too many particles, and that can be very challenging from a numerical point of view. And every time I do the resampling, the particle list will grow and grow. And so I have to have one more step, which is to have a particle joining operation in order to combine particles together while maintaining the state variables in the distribution function in order to reduce my total number. And so after I do that, now I have my new final, resampled field line. And so I have a few tests to show that this is working. And so in the first example, this is with a fluid only solution. And so here I'm using 125 field lines. And on the right, this is with no regridding at all. And you see that the field lines, get bunched in some places and undersampled in others. And that, well, in general, the solution looks okay. You do get some artifacts due to the interpolation and the triangulation. On the other hand, when I include the regridding, I get a very nice uniform distribution of points, and I don't have the same type of artifacts that I do in the non-resampled case. Now, there is one problem with the regridding in that sometimes you can have a situation where some of the points on the boundary end up regridding into the interior of the simulation, and that's something that I'm fixed, but I'm not ready to show that yet. But that's why you see this this sort of bite out on the edge. Now that was an example with just the fluid, but I wanted to show you that this works for the particles too. So this is an example of the outflow solution with fluid and with particles and with superthermal electrons from GLOW. And here this is at one particular altitude slice, and this is showing the O+ distribution at this time, and also the electron temperature on the right. And again, you can see that you get a very nice outflow solution with a very nice uniform distribution of points without any of the bunching that you saw in the low resolution, small number of field line case. So this is a new feature of the code that's going to be coming online very soon, and should improve the outflow solution both in terms of its quality, but also in terms of reducing the number of field lines that you need to follow to get a nice coverage of points. So it should reduce the computational expense of using this type of code. So the other model improvement I want to talk about just very briefly is the need for a better plasmasphere. So in the study I showed earlier in the presentation, we're using the plasmasphere in SIMI, which is this core plasmasphere model on the right, which is solving for the total flux tube content based on empirical refilling rates. And it doesn't give you the density, it gives you the total flux tube content. So you have to make an assumption about how the density varies along the field line. You also don't know the temperature, so you have to assume what the temperature is. And so this pretty limited significantly. And so what we've been doing for a number of years now, I've been working with Joe Huba in order to include improved plasmasphere into this coupling, in particular coupling the SAMI3 plasmasphere with SIMI. And so SAMI3 has a lot of advantages. First of all, we can get a physical refilling rate instead of the empirical refilling rate. It's possible to pass the field line density structure instead of only the flux tube content. So it's many fewer assumptions, a more physical representation. And we did this initial coupling a couple of years ago with an older version of SAMI, and I've recently been working with Joe on getting the updated version of SAMI in there. And so we've done that now. And so the initial coupling is done, and we're working through testing the model with a couple of different cases. This is just one example on the right. This is showing the TEC from the coupled code. So here the potential pattern that you're seeing at the high latitude is being passed from SIMI. In this case, we can take SIMI by itself, or we can take SIMI coupled with BATS-RS to get this potential pattern. And then this is the TEC calculated from SAMI. This is a nice example that Joe put together showing, that the mechanics of the coupling are working. So this is something that I'm very excited about, and I think should, be useful, very soon for improved simulations with a more realistic plasmasphere. And so that's all I had to talk about. So just to summarize, the ionospheric plasma is very important. It's a lot of impacts on the magnetosphere. And when you look at the outflow by itself, there's a lot of processes involved that change the upper and lower limits, and also change, the response to the energy input. So it's a very dynamic problem with a lot of pieces going on. As you saw in Rick's talk a few weeks ago, and I hope you take away from this talk as well, the ionospheric plasma does provide, quite a lot of the magnetospheric population, and not just the cold population, but also the hot population. Now, I only looked at one, test case, and it may be different in other cases, but it's definitely, at least in some conditions, can be a very important contributor to the magnetosphere and can't be neglected. But even the very cold population, the plasmasphere, can have, wide, system-wide, impacts, that can affect the solar wind magnetosphere coupling and other parts of the, and as a result, other parts of the space environment system. And finally, there's some new developments. We're not just running the model as is, but, we're constantly improving the code. And, I just showed you a couple of examples of new things that are coming online that can make better models in the future. And so stay tuned for that. And with that, I think there should be some time for questions. So thank you very much.
Excellent. Thank you very much, Alex. That was a fantastic talk. I can certainly say, as myself not being an expert in some of these ionospheric processes, I've learned a ton just from listening, and I know others feel the same way. Just to quote a comment from John in the talk, it says, "This is a very impressive talk and a great example of numerical simulation for discovery in science. I look forward to reading the paper." So just a plug to definitely read Alex's paper as well, for those who saw the references. And yeah,
Oh,
jumping into the
thank you.
questions here as well. Let's see. So some of the questions, it looks like they may have been at least partly answered in the chat, but I'll just go through in the order they came. So the first was from William Pedersen and says, do you have an estimate of what ignoring the electron neutral and electron ion collisions would be?
The electron neutral and the electron ion collisions.
Or the electron ion. Yeah, and if I didn't state that right, feel free to unmute William in case you want to.
Yeah, Alex, when you in your first slide, you were talking about the chemistry you were talking about in the ionosphere, and you were just talking about ion collisions.
Yeah, I do include the ion electron collisions and the electron neutral collisions. And I do imagine it would have some effect on the result, although I haven't done that study particularly, so I can't speculate. But if you have a hypothesis, I'd be happy to test it out.
Well, I've been looking at Mars ion outflow, and ion and electron temperature is an important parameter. And I haven't figured out if it's an important parameter on Earth yet. And I was hoping you had.
Well, it is true that the formula for the electron thermal conduction does depend partially on the electron neutral collision. And so at very low altitudes where those collisions are high, you can end up, those collisions can reduce the thermal conduction. And so that can end up raising the electron temperature locally. But it turns out I did play with that, and it doesn't have a very large effect on the outflow solution. It creates, some increased heating at low altitude because the thermal conduction can't carry it away. But it doesn't change the large scale solution, because when you get to higher altitudes where the outflow is really forming, the thermal conduction then becomes largely insensitive to those collisions because there's so few of them. And so it doesn't have a big effect. So that's just one example. There may be other cases, but that's just the one that comes to mind.
Sure. Yeah, definitely interesting to think about. And jumping to another question by Eric, says, are you also looking at what happens at other local times? The strange way it all study was limited to the cusp. So it's a little bit earlier on in your talk, if you know what he's asking.
Yeah, no, that's a good point, and I agree. So what I showed was specifically for the cusp, but in the paper that we're writing up, we did another case where we took the field line, instead of going into the cusp, we took it starting on the day side, but then moving through the night side without encountering the cusp. And then, as it goes through to the night side, it's you start, the photoionization is going down, and the field line starts, the density structure starts to collapse a little bit as it goes to the night side. And then it encounters, instead of the cusp, it encounters the aurora. And so there we do the scaling study again, where we're taking this field line that's moved from day side to night side and then encounters aurora. And so that has a different precipitation characteristic, but also has, but even with the same wave heating, you get a different scaling relationship. And so I think that's sort of what I'm trying to say is that you're right. It's different for the cusp and the aurora, and you can't just take a scaling relationship for the cusp and assume it's also going to work for the night side auroral region. That the different initial condition of the field line as it enters the acceleration region, and the different precipitation characteristics and the different photoionization is all going to combine to give you a different scaling for the outflow in the aurora versus the cusp. So that's a good point.
Okay, great, very interesting. And moving on to the next set here, Bill Lotko actually had a couple of questions during the talk. So the first one was, is the O+ outflow flux source limited, i.e. is the max is limited by a number of O+ ions available in the source region, or is the max limited by other factors?
So that's an interesting question. So my supposition was that it was source limited, but it turns out it depends on what you define as the source region. So So if you choose the integration for the limiting flux calculation only above a certain altitude, where you say only things produced above, only O plus produced above a certain altitude can escape, then you find that that estimate seems to match better with the, you know, with the saturation in the outflow flux of O plus. But it turns out that if you move that altitude down for your integration, then that limit goes up. And so my guess is that you're partially limited by what you produce, but you're probably also limited by some efficiency of transport up to higher altitude. And so that, I guess I'm not sure 100% how to answer that question. I do think that the source does provide some of the limit, but maybe not everything.
Okay, sure. And maybe a follow-up with that as well. He had a second question regarding the O plus outflow and says, why is the cusp O plus outflow in the upper left panel effectively absent? Cusp O plus outflow is reported from cluster to be the most persistent source. It looks like most O plus is emerging from the dawn dust sectors where near the R1, R2 currents close. Can you point to any observational evidence for this distribution?
Yeah, so in this case, I assume you're talking about the particular time I was looking at for, you know, for the northern hemisphere outflow, and you do see outflow there where we have precipitation in the model. And so I think that to some extent we're limited by the quality of the electron precipitation that's currently in the code. And so in this case, the precipitation is largely from auroral type precipitation and not cusp precipitation. Now there's new, I didn't talk about this, but there's new work done at Michigan by a student there, Agnet, who is adding improved precipitation models into SWMF. And that's going to give us better representations of cusp precipitation and will let us better target the cusp acceleration. But I think that what the feature you're pointing out is a limitation of the model that we're using.
Okay, great. So moving on to questions in the chat here. Jason Durr had asked, is it known in what way the power law constant, equation 1.49 in slide 16, is determinable from the amount of solar ionizing flux? For instance, if I knew the total amount of solar ionizing flux, could I in principle compute the constant theoretically?
Well, that's basically what we're trying to do here. So, you know, from the observations, you have a power law, like I'm thinking of, you know, from Bob Strangeway's paper, there's a similar paper done by Yiwa Zhang with polar. And in both cases, you find, you know, empirically, you find a power law relationship, but these relationships are really just for the times that are considered and the conditions that are considered. And so what we're trying to do is to determine this type of relationship, not from the observations, but using the model and try and get a little more understanding. And so in this case, we find that, you know, a different solar ionizing flux can yield a different power law relationship. And so if you have observations that you're trying to build this from, you just have to be aware that the power law you find for one case might be different if you were looking at a different day or a different part of the solar cycle. So I don't know how you would make that prediction ahead of time, except by doing the type of study that I presented, but maybe there's another way to do it.
Sure, interesting possibility. All right, next is Pat Reef with a question. Another potential source of the ions to flow upwards, especially in the dusk and open/closed boundary at the upward field line current, is the converging ions carrying the Pedersen currents from the converging electric fields. Can that supply a significant amount of the ions?
I never thought about that before. That's an interesting question, Pat.
Sure, and feel free to clarify, Pat, if you want to restate it or anything.
Yeah, it actually goes along with that ion neutral collision that you're not paying attention to. I mean, that's really what gives you the Pedersen conductivity. And something that we pointed out a long time ago was at the upward field line current region, the ions are drifting towards that region. So that helps you get a source of additional ions because they're coming in from both directions. Whereas in the downward field line current regions, you're actually evacuating the foot of the field line because the electrons are going one way and the ions are going away. So at the downward current sheets, you can actually have an ionospheric depletion locally.
So that's interesting. So we have done in past studies, including the field line current effect, and those are included as well. But I hadn't thought about it in these terms. So rather than answer on the fly, let me think about that a little bit. That's an interesting point.
Sure. Yeah, I can return to that offline as well. All right, so the next set of questions here from John Hajdusek, it looks like some of them were answered, but I'll just go ahead and read it. And so the first one was, if I remember right, He plus is the second most abundant component of the solar wind. About 10 to 20% of the particle population. Is He plus a significant player in the magnetosphere, and does it mostly come from the solar wind or ionosphere? And some initial replies said actually He double plus is from the solar wind, and He plus, just single plus, is not really that abundant. And some other comments kind of confirmed that.
Yeah, I don't have anything to add to that.
Okay, so
I agree.
Certainly. And then the other question that John had asked was, can you describe how you couple the PIC and fluid domains in the PWAM or in the PWAM model?
Yeah, no problem. So, that's so building, I think I spent almost as much time trying to figure out how to couple the PIC and fluid domains as I spent building the PIC model. But basically what happens is the lower ghost cell of the PIC domain is filled by the fluid, by the last computational cell of the fluid. And so based on the density and temperature and velocity, we sample from a Maxwellian distribution particles to launch, to fill that ghost cell. And so those particles, move into the simulation domain of the PIC and get followed. Now, similarly, the first computational cell of the PIC domain provides the upper boundary condition, the upper ghost cell for the fluid domain. And so we can integrate the particle distribution in the PIC domain in order to get density, velocity, temperature, and heat flux. And so it turns out to be a little bit tricky because if you use the density and velocity as the upper boundary conditions for the fluid domain, taking those from the PIC, it turns out that's very good because you end up conserving particle flux, mass and momentum flux through the interface, which is great. But if you use the temperature in the PIC domain, it turns out that you get a mismatch in the heat flux. And so in order to conserve the energy flux through the domain, what you have to do is you have to make the heat flux match. So, in the PIC domain, you have the kinetic heat flux, and in the fluid domain, you have the fluid heat flux, which is a sort of Fourier law approximation, a kappa grad T approximation to the heat flux. And so what you have to do is you have to choose the temperature in order to match the heat flux that's provided by the particle regime. And so in this way, you get conservation of mass, of particle number, momentum, and energy, through the interface, and that allows this coupling to work.
Okay, great.
All right, that was a bit detailed there, but
sure. But as you said, yeah, it's taken a lot of effort to make sure that coupling is happening as well. So very good. And I think that brings us to our last question here. Muhammad was wondering which scale differentiates heavy ions from the lighter ions, and how are these heavy ions identified?
I'm not sure I understand the question. What scale are you
yeah,
talking
feel free
about?
to unmute if you'd like to clarify, Muhammad. if Mohammed's still on the call. Let's see. Yeah, if we're not sure, we can always maybe try and type in the chat for
You
input.
can email me offline. I'm happy to answer. I just don't think I fully understand the question.
Certainly. Okay. Yeah, we can maybe take that one offline. Well, and with that note, for the interest of time, so we had quite a bit of questions there, and want to be respectful of Alex's time too. And I just wanted to echo some of the positive feedback we got in the talk as well. Both Bill had just said, thanks, Alex, really interesting set of numerical experiments, and Ankush had said, great talk, Alex, very much enjoyed. So, so thank you for that. And I just want to let everyone know regarding our schedule for next week, there is a holiday, so we won't be having our seminar as at the usual time, but we'll resume 2 weeks from today on Monday, the 22nd, where we've invited Fran Bagenal, who will be discussing the topic of planetary magnetospheres. So with that, just Alex, want to really thank you wholeheartedly again. This was a great presentation, very educational, and thanks again for your time.
Well, thank you for inviting me, and thank you all for tuning in. I really appreciate it.